I will encourage you to take a look at the paper. The archive number is there. So they actually view this generalized metric space of language as a polyhedron. And these representable functors associated to words are like extremal rays that generate this polyhedron. And so you can kind of see that these representable functors are like the building blocks of more complex words or expressions that sort of live in the inside. And so they explore that in this paper that they had recently. And then even more recently, I think this is interesting. So this is work together with Juan Pablo Vigneault from Caltech. So this is going on the archive like maybe tomorrow or Monday or something. So it's coming soon. So we compute what's called the magnitude of this category. So let me explain this way. Magnitude is a numerical invariant associated to an enriched category that sort of generalizes the concept of Euler characteristic of a topological space, or the cardinality of a set, or entropy of a probability distribution. So it's a number associated to your object that's an invariant of it, all right? Now, for this to work, you actually have to work with finite metric spaces, so there's a way to kind of look at a finite version of the story. And you can get a number, or you can sort of scale things by a parameter t to get a function, a magnitude function, which is more interesting. So what we end up finding is this expression here. So given this generalized metric space of language, what's the function that we get? Well, think of it this way. For every prompt that you can input to your model, there's a probability distributions on tokens, right? So you have a probability distribution. Now, you can take the Salas entropy of your probability distribution. If you do this for every input, you can add all those Salas entropies together. Then you can scale that by t minus 1, where t is the parameter that we threw in. And then there's this other number that I don't want to go too much into, but it's kind of related to the cardinality of the outputs of the model. But I think the entropy thing is interesting. If you do this, this turns out to be the magnitude function of your category. So that's interesting because maybe you're interested in comparing two languages one to another and maybe looking at their invariants, or maybe plotting this function and see what it looks like. So this was an application of something that had been explored in category theory for quite a while with Tom Leinster and Simon Mullerton and many others. And so I think it's interesting to see what this looks like in the context of language. So that'll be on the archive soon. Let me wrap up by saying one final thing. So kind of recap. We started with very little. What goes with what and how often? And then there's all this interesting mathematics that kind of naturally comes out of it. But there's at least one more. There's other things you can do, but let me introduce the final thing that I want to share in this talk in the following way. So remember I just told you about magnitude in the previous slide. Here's how you compute it, okay? You construct a matrix. It's a square matrix. Remember I said you have to make things finite. So imagine you have finitely many strings, and your matrix is indexed by these strings. And what are the entries of the matrix? Well, you take the distance between two strings, scale it by t, and take negative exponential e to the minus t of the distance. Now, if that matrix is invertible, picture the inverse, add up all of the entries in the inverse matrix. The answer you get is called the magnitude. Sounds easy, but that's hard, actually. And so the bulk of the work that we're doing is pulling on some combinatorial work that Juan Pablo had done to compute this number. So, why did I say this? Because there's other things you can do with matrices, right? Instead of looking at a matrix indexed by your strings, maybe you're just interested in like words and their context or something. And maybe you're interested in a matrix whose entries are pointwise mutual information. And you can do things like singular value decomposition on this, and use that for something like word embeddings, like this is a normal thing to do. Another thing you might do is like choose a threshold value, a cutoff value to get a binary matrix. So maybe everything below your threshold in this PMI matrix is 0, and maybe everything above the threshold is 1. So now you can have a binary matrix. Why would you do that? You're losing information. Well, if you do something that is analogous to singular value decomposition, composition, but not quite the same, you land in something called formal concept analysis. And just like SVD gives you a pairing between left and right singular vectors, when you do the analogous construction, really it oversets, this is what's happening. You get something that looks like a concept hierarchy, and you're sort of pairing things that feel like words and their context, or that somehow capturing meanings of words, but from the perspective of lattice theory. So now you have another toolbox with which to explore. And the reason I mention this is because this SVD-like construction, called formal concept analysis, is itself a special case of a more general construction and category theory called the Isbell completion. So you start with a binary matrix and you like turn the handle and you do formal concept analysis. So category theory has an analog of a matrix. It's called a profunctor. And when you compute the crank, you turn the handle on this crank. It's not called formal concept analysis, it's called the Isbell completion of your profunctor. But it's a more general version of this thing. So again, if you take this MATLAB's approach, it turns out that there's a lot of interesting ideas to explore. And so what I just mentioned on the last slide, this is in a paper that came out in the notices of the AMS earlier last year. This is together with Juan Luis Gastaldi and John Torilla, and so we share more about that there. So I think I'll end here, and I hope that I convince you that there's a lot of interesting mathematical structure and language. Category theory at least gives some interesting things to think about. And I think, if one wanted to pursue this more, I might say this could be step 0 and a much longer journey to thinking about mathematical structure and language, but at least it seems like there's some interesting things here.